University of Camerino in Italy. The main topics of interest for him are ultra-cold atomic gases, with particular reference to the BEC-BCS crossover and strongly correlated systems. The title today is going to be Recent Developments in Quantum Fluids. I request Dr. Ayan Khan to please take over.
Thank you, Professor Lakshmiwala, for the kind introduction. So at the beginning, I'd like to thank the organizers of QIQT-2022 and especially to Professor Panigrahi to give us an opportunity to talk about some new recent exciting developments in the field of ultra-cold atomic gases. But as per I understand, these sessions are mostly dedicated to the quantum optics. So I would like to take a cue from there only, because these ultra-cold atomic gases, as I will try to describe, they can be considered as it has legs in 3 different fields, and it actually intersection of quantum optics, condensed matter physics, and atomic molecular physics. So, and it has a wide range of applications. So I will try to go through it, the very fundamentals at the very beginning, because I presume there are some undergrad students might be present, and then we will move towards some recent developments, and in that field, our recent contributions. So let me share my screen first, and then we'll start. My screen is visible?
Yeah, it's visible.
Okay. Yeah, so as the title suggests, it's recent developments in quantum fluids. So the plan of talk is that when we talk about quantum fluids, and as Professor Lakshmi Bala has already introduced me as my primary interest in ultra-cold atomic gases, so I will first get into about the ultra-cold atomic gases. What do we mean by that? And for the students of in the undergrad level, this name may not be familiar to you. So I'll first like to spend a few slides on introducing you to the field of ultra-cold atomic gases and its applications. And then we'll move towards these exotic quantum fluids, which have been recently observed. And then we'll move towards our theoretical contributions in this field. And then I would like to draw my conclusion. Okay. So to start with, the first thing is that what is an ultra-cold atomic gas? So ultra-cold atomic gases are in general considered which are close to absolute zero, that is which is 0 Kelvin. So in general, it's in the order of nano Kelvin temperature. So here you can see in a computer screen, it might appear very small, but what I try to explain here, different temperature scales. And this is here is the ultra-cold atomic gases. And to reach to these ultra-cold atomic gases, to reach there, you need to apply several different techniques using lasers and magneto-optic trapping, which enables you to cool certain alkali gases at this low temperature. And using these techniques, the Bose-Einstein condensate was observed in 1995. And that actually gave a boom to this field, and several research and different perspective, looking at different perspective has started, you can say, from those from that years of 1995 onward. Now, to look into the ultra-cooled atomic gases, so in these temperatures, so at quantum mechanical properties becomes very important. To reach these cold temperature, first the atoms are trapped, pre-cooled via laser cooling, a magneto-optic trap. To reach the lowest possible temperature, further cooling is required using evaporative cooling in the magnetic or the optical trap. Now, in the ultra-cold atomic gases, while describing ultra-cold atomic gases, I have also used a word alkali gases. Why alkali? These are in the periodic table, these are considered the alkali gases. And alkali gases has one free electron in the outer shell. So this figure is taken from the Pethick and Smith's book, actually, which describes the electronic structure. And this actually helps. These are good candidates for the Zeeman effect, and therefore they are very sensitive to external magnetic field. So it becomes much easier to manipulate with external magnet. Now you may ask me, while we talk about Bose-Einstein condensation, and as Professor Lakshmiwala mentioned, my primary interest has been also in BCS-BC crossover. So BCS is the Bardeen-Cooper-Schiffer, the superconductivity. So these Cooper pairing or the Bose-Einstein condensate. But what we're talking about is about some alkali atoms. Now, Bose-Einstein condensate, as the name suggests, it's for bosons. So how do I define what is a boson and what is a fermion in this alkali atom? So what determines is the proton number. If Z is the proton number and N is the neutron number plays a crucial role. So N is the neutron number. If N is even, then boson, and if N is odd, then fermion. For example, lithium-6 is a fermion and lithium-7 is a boson. Why? Because in lithium-6, it is hydrogen, helium, lithium. So it has 3 in the third position in the periodic table. So it has 3 electrons. So it has 3 protons. So lithium-6 mass number means it has 3 neutrons. So odd number of neutrons, so it makes it a fermion. And then lithium-7, it has then 4 neutrons. So the even number of neutrons makes it a boson. Well, so that is how we treat them, and these based on these neutron numbers, they follow the certain Bose or Fermi, Bose-Einstein or Fermi-Dirac status. Now let us come. So this is the very brief introduction to what do we mean by ultra-cold gases and how we classify them as boson or fermion and so on. So now comes the question is what are its applicability. So regarding that, these ultra-cold atomic gases, as I was telling you, it has its connection, very deep connection with quantum optics, atomic molecular physics, as well as condensed matter physics. And that is manifest in its applicational front as well. So ultra-cooled atoms have a variety of applications owing to their unique quantum properties and the great experimental control available in such systems. It is considered as the biggest testing ground for the condensed matter physicist. Simulation of well-known quantum mechanical effects as Anderson localization has already been observed. Real-time exponential decay of the wave function of the density has been observed in Anderson localization using ultra-cold atomic gases. So understanding the physics of high temperature superconductivity, there also ultra-cold atomic gases have been used, because these ultra-cold atomic gases, as I have said, that it is very easy to manipulate and tune their interaction. It is possible to tune from the BCS Cooper pairing kind of a interaction to a composite boson kind of a interaction. And in between comes the BCS-BC crossover, and these crossover physics has some good, it has connection, deep connection people feels it has with the high TC superconductivity. The primary reason of that is that the normalized temperature, critical temperature of high TC superconductors and the BCS-BC crossover comes in the similar range, as well as their coherence length is in the similar range. Okay, so moving ahead, so they have also a very deep application in quantum computation. So these neutral atoms, you can load them in an optical lattice. This optical lattice one can create using counter-propagating laser beams. And in this optical lattice, so this allows as if it is a large register of qubits. So these systems are also being used as analog quantum simulators, which can be seen as a form of special purpose quantum computer. Then moving beyond the ultra-cold atoms, then comes the ultra-cold molecules, context of ultra-cold molecules. So these ultra-cold molecules have recently been accepted as a platform for quantum computation because of their higher degrees of freedom. They can be vibrate, they can rotate, and they can even strongly interact, and which allows the molecules to be more effective in making the qubit to talk. So moving from ultra-cold atoms, people are now moving to the ultra-cold molecules for the purpose of realization of quantum computation. However, our today's discussion not explicitly dedicated to these applications to the towards the field of quantum computation, but it is a little beyond that. And so here we will actually discuss about recently observed some unique phase from obtained from Bose-Einstein condensate, and that is people name as quantum liquid. And I may also touch upon something called supersolid. So the name supersolid may sound very exotic, but I'll try to give brief glimpses on that. So what happened in recent years, in only 2015, Petrov proposed a method to create quantum liquid state starting from a mixture of quantum gases. So you starting from a binary BEC, you can actually land up to a situation where these gaseous condensate can come together and form a bound state, and it can form liquid-like droplets. So this new system is known as quantum droplet and is the result of an effective mean field interaction which is balanced by a repulsive energy provided by the first order perturbative correction. So in these ultra-cold atomic gases, if we calculate the interaction, the weakly interacting ultra-cold atomic gases, so the first order perturbative correction, which in general people ignore, but in certain situations, they may play a crucial role, and that is what is been proposed in 2015 by Petrov. So before that, these beyond mean field term was, though it was existing in theory and it was proposed long back in 1957 by Li, Huang, and Yang, but in practical purposes, they were not used in that vigorously. But after the 2015 proposition of Petrov, an experimentalist also came up and they started looking into the possibility of this kind of liquid-like state formation, which we call as quantum droplet. So quantum droplets in the binary BEC in 2018, that was first time experimentally reported in a science paper. So what happens there in certain situation, my mean field interaction and my beyond mean field interaction, if they are competing with each other, there can be an interaction window where my energy can become negative. And here you see the two competing interactions. And with the these two competing interaction has a region where my energy is negative and the droplet formation can happen. So the droplet-like state in BEC mixture has been observed where they are studied by mixture of two hyperfine states of potassium-39 and assume that the both components occupy the same spatial mode. This was followed by observation of transition from bright soliton to quantum droplets. In the last couple of years, there are several papers came up on understanding the quantum droplet. And I must say, along with us, Professor Panigrahi also has some seminal contribution already made in understanding these quantum droplets. So how to proceed theoretically? We are not doing any experiment here. We are trying to understand it theoretically. And in this lecture, our objective is to present our theoretical approach, which at Bennett University we were doing, and what are the new results we have found in this study of this quantum droplet. So as it has been described, we can start with the binary BEC. As it has been in the experiments, it is mentioned. Now in these binary BEC, so these A11, this E11, A22 are the intraspecies interaction, and A12, A21 are the interspecies interaction. Now, I don't want to make you confused, just to give you a precautionary statutory warning. Here you can see these are this, suddenly some arrows comes up. Here I have written it with some 1122 suffix, but here are these some arrows. That is only to remain consistent with this nice cartoon which has been reported in this thesis of in 2018, which actually encompasses the idea of the formation of these liquid-like state very nicely. This cartoon actually used these arrows, but please don't confuse with spin up and spin down. You can take them as this up arrow, you can consider it as some G11. And down you can consider as G22. And this up down you can consider as some G12. So in binary BEC, a two-component BEC, it is well known that the states are phase segregated if this condition satisfies. If my G12 is greater than square root of G11, G22, then the states are phase segregated and the system is considered as immiscible. Okay. If this minus of square root of G11 and G22 is in between G12 and square root of G11 and G22, the condensate overlaps and the system is called as miscible. Now, if this minus of square root of G11 and G22 is greater than G12, the attractive interspecies interaction overwhelms the repulsive ones, and one on each condensate and the system collapses. But you see, if you take this quantity in this side and consider as some very small delta G, this doesn't make it zero, but it is small delta G where G12 and plus square root of G11 and G22, which contributes a very minute interaction, and delta G is going to zero, we can observe the formation of the droplets, the liquid-like quantum droplets, liquid-like state. So what? So we now take for simplicity, this is a two-component BEC. So for simplicity, we can here in this region we can treat the mixture as an effective single component BEC, and we assume that identical spatial modes for the two components, and that allows us to reduce the two-component equation into an effective one-component equation, along with an additional beyond mean field term which is necessary to stabilize these quantum droplets. So this was the theoretical supporting theoretical documents provided in that science paper, and the following PRL paper by the same group. So what do? We look into this equation, and then we look into there are a couple of another paper by Petrov, and we try, our objective is becomes to analyze the problem in lower dimension. So there is some question is there. I'll try to address this bright solid on okay. So I'll at the end I will keep this question for the time being, and I will try to address it in the later half. I hope that is fine. Okay. So this is a three-dimensional equation, and our objective is to look into in the cigar-shaped geometry, that is in quasi-one dimension, what it happens. In trying to understand that, we realize that there is interesting deviation from the existing theories, which is proposed by Petrov. Petrov, after suggesting the droplet formation in 2D in three-dimensional system, he also proposed with his fellow colleague in lower dimension, and he calculated the dynamical equation of motion in 1D and 2D. Now, in one dimension, according to Petrov's proposition, the beyond mean field interaction has this form, which is mod psi into psi. Now, if we do a systematic dimensional reduction of this equation to quasi-1D, then my interaction is actually mod psi cube psi. This is an interesting difference between a 1D system and a quasi-1D system. Now, you know that in 1D Bose-Einstein condensation is not possible. So physically more amenable system is a quasi-one-dimensional system. So our interest was to analyze the quasi-one-dimensional system, which actually turns out quite non-trivial because of this even exponent of nonlinearity. So here I like to grab attention of the audience that please understand that while studying these quantum liquid in the lower dimensions, specifically 1D or in quasi-1D, there is a significant difference in the nonlinearity, in the nature of the nonlinearity. So it is quadratic nonlinearity for a strictly 1D system, but it is quartic nonlinearity for a quasi-one-dimensional system. This is what we proposed in our article in 2021. So we call this QC-NLSE stands for quadratic cubic nonlinear Schrodinger equation, and CQ-NLSE stands for cubic quartic nonlinear Schrodinger equation. Well, so this is the graph of the, say, some kind of a dimensional crossover you can consider. So this region is 3D. From 3D, with this square root of NAQ parameter, it is less than 1, and here this is strictly 1D. So what we are working on, so this is weakly interacting 1D Bose gas, and what we are working on in this region, in the quasi-1D area. That is our objective, to analyze this area. And then later on, actually, we try to see if there is any analytical continuation. That I will come across in a bit of time. Well, so till now, what I was talking about, I was talking about a two-component Bose-Einstein condensate. But the story is not limited to two-component Bose-Einstein condensate. The droplet-like state before two-component Bose-Einstein condensate was actually observed in the dipolar bees. There, the dipolar interaction and the mean field interaction, when they compete with each other and almost negate each other, at that point of time, a very small beyond mean field interaction plays an important role, and one can observe droplet size. So that was actually proposed in experimentally observed in 2016, and it was said that Rosenwig instability, so quantum ferrofluid, this kind of pattern formation was observed. This is observed for a regular ferrofluid. So this is my ferrofluid. This is a glass over which this ferrofluid is there, and but below there I have a magnet. So this is the nature of the ferrofluid. So this fluid actually makes some kind of a lattice-like structure. Though it is a fluid, but it creates a lattice-like structure. So this is what is called Rosenwig instability. So when ferrofluid is subject to a strong vertical magnetic field, the surface forms a regular pattern of peaks and valleys, and which is called Rosenwig instability. And in these quantum droplets, quantum liquid also, it is possible to observe certain kind of this regular pattern. So in the dipolar BEC, here in the we have, this is my dipolar interaction, and this is my definition of my dipolar interaction, and this is my beyond mean field interaction. So you can observe a quantum droplet using a binary condensate as well as a dipolar BEC, a single component dipolar BEC. Both cases it is possible. And then came the experimental observation of supersolid phase. So while describing the Rosenwig instability, I was mentioning about the pattern formation. So this supersolid sounds very exotic. It is again a superfluid. It remains as a superfluid, but it has the symmetry, lattice-like symmetry. So these are the 2019 papers where the supersolid property was first time reported, but in the dipolar BEC. But before that, in 2017, in the Ketterle group, this was reported for a spin orbit coupled BEC. And very recently came the experimental observation of two-dimensional supersolidity, again in the dipolar quantum. So these are the very recent exciting developments which are happening around Bose-Einstein condensate and with its interaction and new kind of emergence of new kind of fluid, which we call a quantum fluid or quantum liquid, and the supersolid, which is not at all a solid, it's a superfluid, but with lattice symmetry. So this superfluid, this supersolids, a state of matter that has both superfluid and solid properties. It constitutes of particles of supersolid from a rigid ordered structure, but can also flow without dissipating energy. So in recent years, this paradoxical behavior is observed in spin orbit coupled BEC and dipolar BEC, as I mentioned here. So this was for dipole spin orbit coupled BEC, and rest all the experiments were for dipolar BEC. Okay. So now this is what these last 2, 3, 4 years exciting things were happening in the experimental. And we felt very much excited, and theoretically we wanted to analyze, and what we found that there is not much of a theoretical description exists in quasi-one-dimensional, where the nonlinearity, there are two nonlinearities, cubic and quartic. So we divided our approach in two parts. What we did, we thought we divided it in such a way that one part, our objective was more mathematical in nature, and in the other part, it was more physical in nature. So what do I mean by that? So what we do first, we consider a generic kind of a cubic quartic NLSE without getting into the exact physical picture proposed in the experiment. That we don't do. We first take up a generic kind of a second order nonlinear differential equation, which has cubic nonlinearity as well as quartic nonlinearity. Now I know that with only cubic nonlinearity, this equation admits conoidal solution. So we try to insert again the conoidal solution as an unsatz solution, and we try whether we can get any analytical insight through this. What we realize that to have a sustained solution to exist, it is necessary that we modulate the trap also with appropriate conoidal function. So using this conoidal trap potential, we can land up to a CN-like solution. Here, the red line shows the trapping potential in the m equal to 1 limit. And yeah, so this is what we get from the CN solution, and this is for another case we also get this W-like. This is what we get, the bright solitone solution in a conoidal trap, and we can get a W-like solution also in a conoidal trap. We can obtain. But please note that these solutions we have obtained for m equal to 1, and here also we have taken m equal to 1. So when we take it as m equal to 1, it leads m equal to 1 leads to the hyperbolic function, and m equal to 0 leads to the trigonometric. So now here you see this solution actually does not permit any trigonometric solution. If I take m equal to half, the solution blows up. It does not exist. So we can get a localized solution from this analysis. This is what we understood, but we do not get a trigonometric solution from here. And then if we try the same thing with the Sn function, we can get kink and anti-kink solution. Well, here also, if you see, if you put m equal to 0, this becomes a constant solution. Nothing is there. So what we realize from here, from this mathematical exercise, what we realize that the conoidal solution do admit localized modes at m equal to 1, but not sinusoidal modes at m equal to 0. CN solution does not exist for m equal to half. However, same is not true for Sn. The CN solution in m equal to 1 limit leads to bright solitone and W solitone-like structures. And Sn solution in m equal to 1 yields kink and anti-kink pairs. So with this mathematical exercise, we got this information. Now the question comes, so if we want to study supersolid-like state, we need a density wave, and trigonometric solution can be a signature for that density wave. But what we see that the trigonometric solution does not admit here. So what we can do? What kind of situation it can we can have the density wave like solution? So we took an optical lattice then. Instead of any conoidal potential, we took an external optical lattice, bichromatic lattice. The hint we got from the 2017 Ketterle paper, where they have used a super lattice, which was actually superposition of two optical lattices. So we took a bichromatic lattice and we use an external sinusoidal driving force. Why so? Because till now, what we have observed that in dipolar BEC, so the supersolid-like phase is being observed in dipolar BEC and spin orbit coupled BEC. Now, my equation of motion only with mean field interaction and beyond mean field interaction does not capture the whole essence. So for that reason, we need to how we can theoretically or phenomenologically propose a new phenomenologically we try to propose this using an external driving force. Now here I will like to beg pardon to you for just for 30 seconds, as I need to connect my laptop with the charger. It's running out of charge. So kindly excuse me for 30 seconds. Okay, sorry for the delay. So we're using this external driving force as if it can mimic the existence of dipolar interaction or the spin orbit coupling. We are using this force. And using this, we are at the end, we are able to get an analytical solution of trigonometric function, analytical trigonometric solution we are able to obtain. Now, our curiosity was, well, this is fine, we can obtain this analytical solution, but what about if we look into the situation, if we are talking about a dimensional crossover as it is been shown here, there is here we are talking about a crossover regime, dimensional crossover, and we have said that a strictly 1D system has a quadratic nonlinearity, and a quasi-1D system gets we can derive a quartic nonlinearity. So what we thought that in that dimensional crossover, we can have a situation where we have both quartic as well as quadratic nonlinearity. And we try to obtain the solution. Fine. Then we look into an analytical solution with the same setup with only quadratic and cubic nonlinear. Now, what we observe here, these are the observed solutions. You can see for this, this is for this solution. It has been depicted here, and these red lines are these tracking potentials and the optical lattice potentials, and these are the solution, dense periodic density wave solutions. But the interesting part, what we observe here is if you see this quasi-1D solution and you see this solution, they are actually, they come out as same. And even the chemical potential, this chemical potential, we can land up to the same Q1D chemical potential as soon as I take this G3 is 0. What is this G3? G3 is the quadratic contribution. So when quadratic coefficient of the quadratic nonlinearity, if I take it 0, we can easily land up actually in the quasi-1D solution. But the trouble happens that in
strict 1D chemical potential is completely different, as well as my solution is different. So in the dimensional crossover, we are unable to find any smooth transition from quasi-1D to 1D system. And these periodic density wave-like solutions are depicted here. Here is the density, and here we can calculate the current. And so it gives some sense of a idea of a super solid-like phase with external driving force. By mimicking external driving force is mimicking the experimentally used dipolar situation or spin orbit coupled situation. Now, if we summarize this, what we find the existence of these sinusoidal modes in presence of external periodic driving force and optical lattice, and Q1D and Q1D1, these two wave functions are same, but this is not the same. So the solution necessitates a bichromatic lattice for Q1D geometry, and while in 1D, simple optical lattice is sufficient. That is another point to know. In 1D, with a single optical lattice, we can have a sinusoidal solution. And the chemical potentials also see a connection for Q1D and Q1D1D region, while in 1D, the chemical potential is quite different. Okay, so these are some takeaways from our mathematical exercise. Now let us look at the problem from the recent experimental perspective, and we try to work on the theoretical description with the experimental findings. So again, we go back to the already described equation, which has been described in the PRL paper in 2018, and we do a systematic dimensional reduction of this equation of motion. And these are the standard procedure of dimensional reduction, and the quasi-one-dimensional equation will look like this. Here I have a quartic nonlinearity, I have cubic nonlinearity, this is my external potential. Now for simplicity, initially we consider that my K goes to 0. So that is some kind of a quasi-homogeneous situation, or while K is very weak. And using this ansatz, we are actually able to obtain analytical solution, which was in the cubic quartic NLSE. To the best of our knowledge, we were the first time, so we are able to propose it. But this solution is quite constrained, as this solution is only possible if the mean field and beyond mean field interaction follows either this condition or this condition. That is, the beyond mean field interaction, either half of mean field interaction or 1/3 of mean field interaction. Well, using these, these are our analytical solution. And then when we do the stability study, we find that the second solution comes out to be stable. And you can see now this flat top-like state, which is a signature of droplet-like state. So this is a fixed density. So density becomes fixed here, constant here for a larger spatial dimension. And these are my localized solution or bright soliton-like solution, density bright soliton-like solutions. And these we obtain for lower particle number. So what we observe is that at lower particle number, we have localized solution or bright soliton-like solution. And for relatively higher particle number, that is n equal to 10 or n equal to 20, we observe droplet-like state. So as the particle number increases, the gaseous BC, which is manifesting a soliton-like behavior, they come together, form a compound pairs, and it starts behaving like a liquid. So this is actually from where we got the particle number. This is the equation for the particle. Well, so we then verified our analytical solution with the numerics. And after verifying it, now the numerics, we also did the modulation instability study for this type, for this problem. And these are the regions of, so this is this gamma. Here I have this gamma, which is imaginary of this omega, where omega is this. So gamma not equal to 0 is then omega is complex, and which leads to the unstable areas. Well, and so these are actually the stable areas, and this is the instability. We do the modulation instability study. Well, as I was talking about, so if we now look more physically in this problem, so this is my mean field energy, and this is my beyond mean field energy, and this is my mean field energy, where mean field energy is attractive and beyond mean field energy is repulsive. And that effectively, this is kind of a cartoon I have drawn. So if it creates an effective energy, which is a negative, and this region we call it equilibrium density. This equilibrium density we obtain where the pressure is 0. And from this region, this bright soliton starts converting into a liquid-like state. And this is my critical density, beyond which again the liquid-like state starts falling apart. And with our analytical result, we see that this is actually, we obtain numerically this solution. Using this solution and solving these particle number equation numerically, we see that when we calculate the effective energy, our results fits quite well with this analytical argument. So what are the takeaways from here? That the two analytical solutions of CQ NLSE was obtained and numerically verified. One solution is stable in a given parameter region. Polytonic and droplet regions were discussed by calculating critical and equilibrium density. And the unstable region under modulation instability points to the low density region where bright soliton formation takes. Well, then question comes to here, we have considered my K is equal goes to 0, or that is there is the external potential is 0, K going to 0, and we obtain the analytical solution. But we can always do numerics with the trapping potential. So this is the plot for K equal to 0.1, K equal to 0.01, and K equal to 0.00001. The different trapping strength we have tried to plot. And what we observe in the quasi-homogeneous region where K is very small, we see droplet-like flat top, and then a relatively stronger K, we see a bell-like solution, and then further stronger K, we see again localized solution. So here, actually modulating external trap, we can move from a droplet-like state to a soliton-like. So this indicates, this motivates us to look at the energy there. And we see surely the energy is negative. In this region, chemical potential and energy is negative in the when the trapping potential is very weak. And this region we put a shade here as if this is kind of a transitional crossover, it appears to us, because this nonlinear, non-monotonic behavior does not have any abrupt change, does not show any abrupt change, but they're sufficiently smooth non-monotonic behavior. So we consider this region as some kind of a droplet to soliton transition crossover. Well, when we calculate the droplet size, this is the droplet size, and we see a very smooth transition from droplet-like region to solitonic-like region. And these squares and dots, these are nothing but for different interaction values. Different kappa, that means G by G prime, that is the ratio of the mean field, ratio of the beyond mean field to the mean field in. So this interaction change, this actually does not affect much in case of the droplet size. And this is actually, we have normalized it to the peak droplet size, the maximum droplet size here. Well, then we looked into the role of the particle number. And we tried to make a phase diagram, and you see at the very low low interaction strength, the peak density remains constant, which is the signature of the droplet-like state. And then it grows, and which is moves to the localized state. And when we look this, try to make this figure for with respect to particle number and my interaction, the trapping potential strength, this is what we observe. So this region is my droplet-like region. This is my crossover-like region. And this is my polytonic region where density is increasing much faster. So these were the final takeaways for us from here, that the tuning the longitudinal trap, we observe a droplet soliton transition. The transition is smooth. That's not a phase transition, rather a crossover. And droplet on soliton phase diagram as a function of a trap frequency strength and particle number. We prepared a phase diagram with the particle number. Well, so let's now draw the conclusion. So what we actually tried to explore here, that we tried to explore the thread between the quantum technology and ultra-cold atomic gases, then discuss the recently observed exotic quantum fluids, explicated the theoretical framework for a quasi-one-dimensional geometry, presented the analytical and numerical solution, investigated the possible droplet on soliton crossover, and introduced an analytical scheme to realize supersolid-like force. So these were the main takeaways or main summary of what we tried to cover. And here I like to take this opportunity to thank Mr. Argo Devnath, who is the research scholar doing PhD with me, and Mr. Jammu Todun, who was undergraduate project. Some of his project results but later came out as a paper. And Professor Saurabh Basu from QIQT-2022, the last work was in collaboration with him. Also, I'd like to thank for the funding agency, BST SCRB. Thank you very much for your kind attention.
Thank you, Dr. Ayan Khan, for a very instructive lecture. I think even people who have not been in this area would have learned quite a bit from here.
Thank you very much.
Any questions? I don't see any questions in the chat box except the first question that was put there.
Yeah,
what do you mean by a bright soliton?
Yeah, so already I think I have discussed the bright soliton part. Yeah.
Are there any further questions from the audience? I just need some clarifications, if it's all right. In the Petrov model, of course, you just look at the first order perturbations.
Yeah.
How negligible are the higher order perturbations?
Yeah, so that is the next point. So you know that this, even the first order was not considered till 2015. Never it came.
No, but it seems to have made a lot of difference.
It has made a lot of difference. So now it can be really exciting to look at the higher order. So of course that can be the next step. So till now, I don't think people are very much busy in exploring these with this first order effect itself, and so much rich physics is coming out of it. I haven't seen any article till now with this further higher order, but of course it's worth checking.
The other thing I wanted a clarification from what I understood in the supersolid-like phase.
Yeah.
Either it's spin orbit or dipolar BEC.
Yeah.
There are no external. Yeah, but there are no external driving forces there, right?
No, there are no external driving forces.
But you seem to think that the external driving force mimics this, or effectively,
yeah. So as I have said, I started initially with as some mathematics. It has two parts: a mathematical part and a more physical insight. So initial part, it's a more of a mathematical part as a mathematical exercise. And when I find that I cannot get any sinusoidal modes or trigonometric modes, I said how we can have a trigonometric mode. So I used a periodic driving force borrowed from some idea, some papers. This idea was borrowed from some papers of Professor Panigrahi only. And using that, I can see that, of course, these we can see as the sinusoidal mode solutions. So these very much generic. I have kept these external force as a driving force is very generic, and some, as I have said, phenomenological. But that actually, I have talked with other people also, and there means the spin orbit coupling also can be mimicked. Means it can be considered as an additional force. So physically, it is much more general, simplistic model, you can say. Of course, not accurate. It's a very simplistic, and with theoretically, it maybe in the coming days we'll get into a more physically relevant theoretical description.
Yeah, it would be interesting, because if the textbook spin orbit coupling in nuclear physics can be replaced by an external driving force, that's a very interesting approach.
That might be a little bit outrageous.
I don't know. Anyway, are there any further questions? And I also request the audience to just talk through the mic and ask questions if you have any. Okay. If there are no further questions, I thank Dr. Ayan Khan for a very instructive lecture. Thank you very much.
Thank you very much.